Hello everyone. We've done a couple of exercises. Well, not a couple. We've done several exercises on linear equations, and we came to be we familiarized ourselves with substitution and elimination. So any function that has the powers of something, that's not really a linear equation. So linear equations, basically to the power of 1, and you can get as many variables as you want or can. So you have 2-dimensional and 3-dimensional function systems. So when you have two functions, that's what you call a two-dimension system. And then when you have 3 functions, 3 variables, that's when you get the 3D system. Anyways, and you can get, of course, more. But the primary thing to say here is that when you solve for these equations, you can go for substitution. Either if it's 3 equations, you substitute one for another, and then you eliminate one, and then you do the same for the other one, and that's basically how you do it. And you can see here, this was been done here, and then you solve for z, and so yeah. So that's the elimination. The substitution, we've already seen that. You substitute one for the other, and then let's quickly check it out. Solving by elimination. This is solving by substitution. So you got these 3 equations. Now you set 1 to be x would equal to something, and that's what it is here. X equals to this, and then you do the same for the second one. You apply the x in the third equation. It's the x on the second equation. Keep in mind that the first one remains as is. So you get this. So that's 12. Move to the other side. That's 3. Then you got negative 2z plus 3. That's 1z, and then the y. That's what you get there. Now we either set this to be y or to be z, so they set it to be z, and then you apply the 3y in the second equation. And if it was the second equation, if we had an x here, we would also substitute it here as well, or any of the equations, just to get an x and a z. So we have the z and we have the x. We apply them here to get the y. So that's the value of y, you get the z, and then you get the x. The elimination, however, you take 2 functions together, you eliminate one, that's a new function. You get basically a new function, and then you get another 2, and then you get another new function. And that's about it. Okay. So we've done that. I'm not sure what... So we've done this. I think we could go on with the rest of the videos. Matthew, let me open up that channel and follow on with the rest of the videos then. Before we do that, so this is the linear equations. This is something we've seen already. And then we work with the slopes. That's something that we've also seen. Working with the slope. Equation of a straight line. That's something we've also seen. And then slope of a straight line. That's something we've done just a second ago. Yeah. So that was about it for straight lines. Equation of a straight line. Okay. Let's see the index again, just like quickly. What is it talking about? Equation of a straight line. Just need to check the index here. Okay, so actually it's not important. Math graph index. So let's see. Anyways, let's go with the rest of the Matthew video.
Hello, I'm Professor Von Schmohawk, and welcome to Why
I think
You.
we've already seen this video.
So far, a number of solutions, and this solution, how the results differ.
Yeah, I've already seen
whose
this.
graph is composed of three planes.
I think we've already hit around. We've done the 3D planes, so no solution. So basically, it's the same as to what we've already seen. So let's see what he's talking about.
Intersecting at a single point.
Yeah.
We saw in the previous lecture that systems like this can be solved using the same basic techniques we use to solve systems of two equations in two variables. We start by choosing two of the three equations and eliminate a variable, giving us an equation in two variables. For example, this time we'll use the first and third equations and once again eliminate z. By choosing two of the three equations and eliminate a variable, giving us an equation in two variables. For example, in this system, let's eliminate the variable z using the first two equations.
And then use the first and the third equation.
Gives us. Now that we know the value of x, we can set x to 0 in either of the two equations we just added and solve for y. Setting x to 0 in the first equation,
You do the substitution basically.
know that the solution is unique. System. But what will happen? This solution can be written as the ordered triple 0. The infinite number of points on this line correspond to the infinite number of solutions of this system. First and third equations to produce a number, or dividing by 4, multiply the second equation.
So I believe when they are all zeros, that's when you get infinitely many solutions. And then when you have different illogical answer.
Hello! Number of solutions.
Yeah, so what we've got.
As a general rule, if we start with equation 0 equals
so the
0,
result of the two equations, that is, of course.
that obtaining an
I'm not sure what's wrong with the connection today. It's pretty terrible. I'll try to connect to another connection.
hello! The use of x and y.
So this has no. So
If we start with a system of three linear equations and three variables, and by eliminating variables we obtain an equality between two unequal numbers, such as 0 equals -1, then this indicates that the system has no solutions. As you may recall, obtaining an equality between two unequal numbers also indicates the same thing in a system of two linear equations in two variables.
correct.
And we saw earlier that obtaining an equality between two equal numbers indicates an infinite number of solutions. However, in systems of three linear equations and three variables, it is possible to obtain both results. In other words, we can obtain an equality between two unequal numbers and an equality between two equal numbers in the same system. This can happen when two of the equations describe parallel planes, and the third equation describes a plane which is identical to one of the other planes. During the process of eliminating variables, the pair of equations which describe the parallel planes will produce an equality between two unequal numbers, indicating no solutions. And the pair of equations describing identical planes will produce an equality between two equal numbers, indicating infinitely many solutions. However, an indication of no solutions
means no
always
solution.
trumps an indication of infinitely many solutions, since there can be no solutions for any system which contains parallel planes.
No solutions would win. Okay. Fair enough. We've already done that. Let's jump to parametric equations.
Von Schmohawk, and welcome to YU. So far, we have seen how to describe a single unique solution in a system of three linear equations in three variables. We can describe the solution either by using three equations or represent it as an ordered triple, which gives us the values of the x, y, and z coordinates of the solution point. We have also seen that if during the process of solving a consistent system of equations, we obtain an equality between two equal numbers, then this indicates that the system has infinitely many solutions. However, we have not seen how to describe what these solutions are. A system of linear equations in three variables has infinitely many solutions when all the planes in the system intersect along a line, or when all the equations describe identical planes. So when a system of equations has infinitely many solutions, to describe the solutions, we must first check to see if the equations describe identical planes. Fortunately, it is easy to spot this condition, since when the equations are written in standard form, ax plus by plus cz equals d, any equations which are multiples of each other will describe the same plane. Therefore, if the equations in the system can all be made identical by multiplying by constants, they all describe the same plane. In this case, the solution set of the system is
This is important to you.
distance.
I'm going to write it down here.
Therefore, if the equation is described by any of the equations. However, when all the planes intersect along a line, then this solution set is not described by any of the equations. We need some other way to describe a solution set whose graph is a line in three-dimensional space. Since a line in three dimensions is a linear object, you might think that it could be described by a linear equation in x, y, and z. But as we have seen, linear equations in three variables describe planes, not lines. In order to mathematically describe a line in three-dimensional space, we need a way to define the values of the three coordinates at every point along the line. This can be done by creating a group of parametric equations, one equation for each of the three coordinates. Each parametric equation expresses expresses the value of one coordinate as a function of an additional variable called a parameter. In this
Parametric equations with an S.
example, we have chosen the letter t to represent this parameter. For any given value of t, each of the three parametric equations determines a corresponding value for one of the three coordinates. For example, the values of x, y, and z could be equal to t, t plus 1, and 3t minus 3. t t plus 1, and 3t minus 3. So each value of t corresponds to an ordered triple, which describes the position of one point on the line. In a parametric equation, the parameter varies freely over some defined range of values. Since in this example, the line representing the solution set extends infinitely in both directions, the parameter t must vary over all real numbers. If we think of t as representing time, then we can think of the line as the path of a point whose position in space is a function of time. Perhaps this is why the letter t is often chosen as a parameter name. So a solution set corresponding to a line in three-dimensional space can be described using three parametric equations. Or it can be represented as an ordered triple, where the values of x, y, and z are each expressed as functions of a parameter. It is also possible to use one of the variables as the parameter, expressing the coordinate values in terms of this one variable. These are all examples of ways to write parametric representations of the solutions to a system of equations with infinitely many solutions. So in solutions to a system of equations with infinitely many solutions. So when the solution set for a system of equations in three variables is a line, how do we calculate the parametric representation of that line? In the next lecture, we will demonstrate how this is done.
So how do you calculate them, which is 47?
Von Schmohawk, and welcome to YU. In the last chapter, we saw that when a system of three linear equations in three variables consists of three planes whose intersection forms a line, the system has infinitely many solutions. And these solutions can be described parametrically using either parametric equations or an ordered triple. To demonstrate how this is done, we will start with a system of three equations which describe three distinct planes that intersect along a line. When solving a system of equations using the elimination method, we typically start by eliminating one of the variables. So let's say we choose to eliminate x. To eliminate the variable, we pick a pair of equations to add, first multiplying one or both equations by a constant if necessary to make the sum of the x terms 0. In this example, we can pick any pair of equations, so let's select the first two equations and multiply the second equation by -1 in order to make the x terms cancel. Adding the equations, we get 10y plus 10z equals 10, or dividing by 10, y plus z equals 1. Now we pick a different pair of equations and eliminate the same variable x. This time, let's pick the first and third equations. The equations, we get 6y plus z equals 1. This gives us a system of two equations and two variables which we can try to solve to determine the values of y and z. But since both equations are identical, when we multiply one equation by -1 and add the equation,
My connection is terrible today. I've connected to another router, so let's see if that helps.
we get 0 equals 0, indicating that the given system has infinitely many solutions.
So far, so good.
We have seen that eliminating x using the first and second equations gives us y plus z equals 1, and eliminating x using the first and third equations also gives us y plus z equals 1. Will we always get the same result no matter which pair of equations we choose? Let's see what happens if we use the second and third equations to eliminate x. Multiplying the third equation by -1
Sure, it doesn't give you
and adding the equations,
oh yeah, it does.
or dividing by -4, we once again get y plus z equals 1. So no matter which pair of equations we choose,
You always get the same result.
we always get the same equation, y plus z equals 1. And therefore, we will always end up with the result 0 equals 0. The equation 0 equals 0 contains no information other than to indicate that the given system has infinitely many solutions. However, the equation y plus z equals 1 can be useful in creating a parametric representation of the solutions. Since it contains only two variables, it makes it especially easy to create parametric equations for y and z. and therefore we will always end up with the result 0 equals 0. The equation 0 equals 0 contains no information other than to indicate that the given system equals 0.
So the problem is my browser, not the internet.
Substitute t for z in the
Okay.
We create the first parametric equation by equating either y or z to the parameter t. Depending upon whether we choose y or z, we will get slightly different parametric equations. However, even though the resulting parametric equations may be different, they describe the same line. For this example, let's equate the variable z to t. Remember that we need one parametric equation for each variable x, y, and z, and each equation equates that variable to a function of t. Our first example, let's equate the variable z to t. Remember that we need one equates that variable to a function of t. Our first parametric equation, z equals t, equates z to a function of t, albeit a simple function. Since z is equal to t, we can substitute t for z in the other equations. We can substitute t for z in the other equations. Now t for z in the other equations. Now we need parametric equations for x and y. Since the equation y plus t equals 1 contains only the variables y and t, we can use it to express y as a function of t. Subtracting t from both sides, gives us the equation y equals 1 minus t. Now that we have parametric equations for y and z, we can create a parametric equation for x by substituting 1 minus t for y in any of the three original equations. Since all three equations contain x, we can use any one of the equations to create a parametric equation for x. So let's choose the first equation. Replacing y with 1 minus t, we can now solve for x. We start by distributing 8 to the terms in parentheses. And combine like terms, giving us 3x plus 8 minus 4t equals 18. Subtracting 8 from both sides, we get 3x minus equals 10 plus 4t. X, we now have parametric equations expressing x, y, and z as functions of t. The solution set can also be represented parametrically as the ordered triple 10/3 plus 4/3 t, 1 minus t, t. This ordered triple describes the line of intersection of the planes and the solution set of the system of equations. During the process of eliminating x, we found that no matter which pair of equations we use, we always produce the same equation y plus z equals 1. Therefore, when we eliminate another variable, we will always end up with the result 0 equals 0.
Just modify the point here. Eliminate.
If instead of eliminating x, we had chosen to eliminate y,
It will always yield the same results.
each pair would have produced the equation 3x minus 4z equals 10, and we would still end up with a result 0 equals 0. Likewise, if we had chosen to eliminate z, each pair would have produced the equation 3x plus 4y equals 14, with the same end result 0 equals 0.
So it's always the same thing.
So no matter which variable we eliminate, and no matter which pair of equations we use to eliminate that variable, we will always end up with 0 equals 0, indicating that the system has infinitely many solutions. But it turns out that even though eliminating different variables produces different equations, as long as we start out by setting z equal to t, the parametric equations will be the same. It is important to remember that there are an infinite number of parametric equations which can describe the same solution set. In fact, we would have ended up with different parametric equations if instead of setting z equal to t, we had set x equal to t or y equal to t. These changes would have produced different parametric equations and different ordered triples. However, these different parametric are all valid and would still describe the same solution set. There is no single unique set of parametric equations for a given solution set. Many different parametric equations can describe the same solution set. The point described by different equations may lie at a different position on the line for a given value of the parameter. Likewise, as the value of the parameter changes, the point described by different equations may move along the line at different rates. But although the equations may be different, as long as they describe every point on the line, they are a valid description of the solution set. In this lecture, we have seen that a solution set corresponding to a line in three-dimensional space can be mathematically described by parametric equations. And we have seen how these parametric equations can be calculated. We also saw that in systems containing planes which intersect along a line, when we eliminate a variable, the same equation will always be produced, no matter which equations are used to eliminate that variable. In the next lecture, we will see why this happens by looking at the process of variable elimination geometrically.
Okay, so I think we've covered a pretty good chunk of information today. Well, it's quite simple, to be honest. There's not a big deal in this case. So to quickly recap on what we've done, so we're just done with the so to describe the infinitely many solutions, we need to use what is called parametric equations, in which each of the variables, because as you're describing a line, you're not really describing a plane, and an equation of three variables is used to describe a plane, and in our case it's a line. So each of the points has to be described with its own function, linear function of a single variable. So we assume the function of t, and then we start off eliminating two equations at a time, and then we get you will always get the same equation regardless of the two equations you use. It's always the same results, whether you start eliminating with the first two, or the second two, the first and the third one. Regardless, you'll always end up with y plus z equals 1 if you are eliminating for x, of course. And then once you get that, you assume one of the variables would equal to t and substitute accordingly, and per our equations, and each time you substitute the variables in the equations, you solve accordingly, and you will get the parametric equations. Now, the parametric equations not necessarily are the same throughout. Now, in this case, it's just because we chose z equals t. Now, if we chose x equals t or y equals t, we'll get different set of parametric equations, but they will all serve the same solution set. Okay, so let's see why these equations, when eliminating, yield the same results in the next video.